Alright, so we're looking at our parallelogram properties 510. So just as a reminder of parallelogram properties, we have our parallelogram, and again the properties are emphasized on the far right there based off the diagram that's provided, where you have two pairs of parallel sides that of course never intersect and or cross. And we're still going to use those properties even now, even today. So specifically, again, opposite sides are parallel, opposite sides are congruent. We also know that consecutive angles are supplementary, and the diagonals bisect each other, so I could just add these additional markings here as well, just to emphasize that opposite sides are congruent to each other, as well as being parallel. And then the diagonals are clearly marked as being bisected, of course. So you have a nice diagram that represents that. And of course, there are additional properties for rectangles, rhombi or rhombuses, and squares, and all of those are parallelograms. So there is a shape hierarchy that we've kind of discussed. We use circles in general to emphasize this hierarchy, but the main, I would say, overruling supervisor of all of the different quadrilaterals is, of course, just that it's a family of quadrilaterals. And you break it down from there into whether they are trapezoids, or if you're in the UK, you can call them trapeziums, or kites. And specifically, when you're looking at a rhombus, a rhombus in some regard is a form or a type of kite in a sense. We just want to be careful that it's not representative of all kites. But you have this family of parallelograms right here that we've seen in the past, right? So all of those are parallelograms. The other quadrilaterals, there are shapes that are not. And so they're kind of on their own a little bit. So as far as it being, a rectangle, then it's a square, and then therefore you have the figures like in more, how best to describe it, the square represents the figure that has all of the properties of any of the parallelograms that I circled there, which is why you see it as the innermost circle. However, rectangles and rhombuses are not the same shape, which is why they're not necessarily one inside of the other. Of course, you also have a trapezium on the far side there, because trapezoids are, by their very nature, not parallelograms, so they don't have the same properties. Okay, so that being said, why isn't a trapezoid a parallelogram? Well, the answer, of course, is that it's not a parallelogram, as I just said. But the reason why is very simple. It has only one pair of opposite parallel sides. It has to have both pairs. It needs two pairs. And it doesn't have that. So the other side, which are called the legs of the trapezoid, those are not parallel to each other. So again, that's why it's not a parallelogram by definition. Now, a special type of parallelogram, as you already know, is the rectangle in particular. And the rectangle, of course, has the properties of a parallelogram, but it also has two additional properties, which is that the diagonals are not just bisecting each other, they're also congruent. And as you can clearly see, they've marked every single one of these halves of each diagonal with 3 tick marks, because they are going to be congruent to each other. The other thing, of course, as you can see, is that a rectangle also has 4 right angles as well. So we want to kind of explore the relationship between those types of features, which are outlined in the white boxes that you see there at the bottom. So, which statement is not a property of a rectangle? A diagonal forms 2 congruent triangles. Diagonals are congruent. Diagonals are perpendicular, and opposite sides are parallel. So what's interesting here is that when you're exploring the first option, forms 2 congruent triangles, in this particular case, we know the opposite sides are congruent, and we also know that you have a right angle here and a right angle there. So when exploring diagonals, depending on which triangle you're trying to look at, take a look at this single diagonal right here, for example. This diagonal does in fact create congruent triangles because you have side angle side congruence. As an example, that's not the only one, but it's one of them. So as I'm illustrating there, that actually is, that's a true statement, right? I want to use T for true. Are the diagonals in a rectangle congruent to each other? Well, we just talked about that. That is actually true. Are they perpendicular? That is not true, actually. In a rectangle, the diagonals are not perpendicular necessarily, right? If it's a square, then they are, but it's not here. It's just a rectangle, so that's false. Opposite sides have to be parallel because it is a parallelogram. So the one, of course, that's false is this one. This is one that's not actually a property. That is a property of rhombi, which is plural for rhombus, and squares, but that is not a property of rectangles. So rectangle diagonals, of course, as you know, are congruent to each other. And just summarizing everything they're saying here, I just want you to keep in mind these are all four equal to each other. That's the key that I want us to take away from that. They're all equal to each other. So when looking at an example that involves diagonals, we already understand that AE is being provided as 5x plus 3, and BD is the entire length across for the diagonal. So we know that we can find the value of x because if we double AE in this case, as we're saying right here, that'll equal the full diagonal length of BD. So we can go ahead and we can, there's two things you could do. If you want to distribute because you might be formally trained to do that, then certainly you can do that. 10x, of course, plus the 6 equals 12x minus the 2, where you would then subtract the 10x, and you would get 2x minus the 2. You would add 2 to both sides, so here we get 8 equals 2x, and you can see that after dividing by 2, you get x is equal to 4. So if we want to figure out the value of x, certainly we could do it that way. The other step that you could do as well, if you wanted to at this particular stage right here, is you could just divide both sides by 2. So you get 5x plus 3 equal to 6x minus 1. And if you solve that equation, you're going to end up with the same thing. You're going to get x equals 4. So that's an example of where we're using the properties of a diagonal, diagonals in a rectangle. As you might imagine, you can pause the video here and see if you can come up with an incorrect statement based off of what they've given us. So they've told us that this is a rectangle, and they're saying that BCD is equal to 90 degrees. Well, that refers to this entire angle over here. That's actually true. AE is equal to DE. So this is a rectangle. So that means these are all four equal pieces. So AE is referring to this length right here. DE is referring to that length right there. That is also technically true. BE is the last one. BE equal to AC. That one actually is false. That's the false statement because BE is actually only half a diagonal, whereas AC is the entire diagonal. So that can't be true. The other one, of course, is CBD. CBD is going to be this angle right here, and ABD is this angle right here. These angles combined, of course, they're going to be complementary because they form 90 degrees, so that statement actually is also true. So this is the false statement. So rectangle right angles, right? We know that an angle at a vertex of a rectangle is 90 degrees, so if we have a particular expression for that angle, we can substitute that in right here and solve for the variable x to find the value of x that makes that so. So as an example, they're telling us that BAC is this angle right here, and they say it's 3x plus the 10, and this angle right here, they're saying that this is 2x. So what they can do is they know that they're complementary angles because their sum is equal to 90. So they're substituting 3x plus 10 in for BAC, which you can see right here, and they're substituting 2x for CAD, which you can see right here. And then they're combining like terms and solving. This was an example we'd already used in the past when we talked about rectangles earlier on the previous week. So just keep in mind that they're just substituting and combining like terms and solving for x using algebraic operations because they know that those angles are complementary, meaning their sum is equal to 90. Lastly, we have a rectangle right here where they're telling us in the rectangle ABCD, we know that CDB is this angle right here at 5x minus 10, which is this angle, and ADB is this angle right here, which is 4x minus 8. Notice that I'm not assuming that they're equal. I'm using different arc marks because this is a rectangle, right? So the diagonals do not bisect opposite angles here. That's not what's happening in a rectangle. But what I do know is that their sum is going to end up being 90. So I can replace those measures that I have here with those expressions. So CDB is 5x minus 10, and ADB is 4x minus 8. And that is going to have a sum of 90. So I can combine the like terms, of course. So I have 5x and 4x, and that equals 9x. I can combine negative 8 or negative 10 and negative 8 because they're both negative values, and I get negative 18 equal to 90. Then I can go ahead and add 18 to both sides, and we end up with 9x is equal to 108. And then I can go ahead and divide both sides by 9. So therefore I get x is equal to 12. So to find the value of x, we found out that it was equal to 12, and we've done this example in the past as well in the previous week. So those are complementary angles because their sum is equal to 90, right? The whole angle there has to be 90, so sum of the parts equals the whole. The two angles together will have a total of 90 degrees. So I'm just combining them together. I would certainly recommend you refer to these examples or this example. And of course, there's another slide that also demonstrates it as well that can help you on your exit ticket, of course. So speaking of the exit ticket, here is your exit ticket. In the first problem there on the left, we have rectangle ABCD, and they're telling us that AE is 3x minus 1 and that DE is 5x minus 7. So the best tip I can give for you here is to go back to your reference slide for rectangles and remember what we talked about. We talked about the fact that the diagonals of a rectangle are going to be congruent to each other, right? So in this diagram here, you see how we have 4 different equivalent lengths, right? So these are all what we would refer to as half segments. They're all equal to each other, right? How can I use that information to assist me in writing an equation that will help me represent the solution to this particular problem? And of course, there are examples that we've worked on in the past. For example, this example is similar, right? Except we had half a length and we had a whole length. So we had to utilize a specific equation here to solve that value for x. What would I have to do to that equation if I only wanted half lengths, right? If this was set equal to that, what would I have to end up doing? That's the question, right? How would that change your equation? So I'd recommend you refer to that and think about how we know the diagonals are all congruent to each other. How can I break them apart, set up an equation, and solve? Also pay attention to the fact that it's asking for the length. It's not just asking for x. The diagonals of a rectangle ABCD intersect at point E if AC is equal to 8x minus 6 and DE is 25. I highly recommend that if you have a rectangle drawn, drawing a rectangle can be extremely helpful because you have the ability to label, right? So you have A, B, C, D, and I would recommend you label it because that can help you understand better what's going on, right? So you have a diagonal AC, and then there is an intersection point between the two diagonals that they're referring to as E. We have an example a lot like this, okay? So if I give you the entire length of A to C, and I give you the half length of D to E, how can I write an equation that solves the value of x? Again, that one slide I was just on is a perfect example of what I would be referencing. So it's really good for those first two questions. And then the final question there, we have rectangle PQRS, angle RPQ. RPQ is 27 degrees right here, and they're wanting RPS. So they want this angle right here. And you already know what the total angle needs to be in that particular diagram. So I leave it to you to correctly find the missing angle portion because you already know what the total at the corner has to end up being. That's going to be our lesson on parallelogram properties 5.10.